Today, we're going to decode the language of information itself. We're going to explore how basically everything, from a simple thought to a complex video, gets translated into signals that can travel all over the world. So let's dive right in.
It's a really great question, right? Before any piece of information can be sent anywhere, it has to be converted into a language that our technology can actually understand and transmit. And that whole process involves two absolutely critical steps. First, you got to turn that information into data, and then second, you turn that data into a signal. So let's kick things off with the most fundamental concept there is, the difference between data and the signals that carry it. You can think of data as, say, the letter you want to send. And the signal? That's the mail truck that actually delivers it. They are totally related, but they are not the same thing. Now, data itself comes in two main flavors. Over on the left, we have analog data, which is continuous. Think about the smooth, gradual change in the brightness of a sunset. There's literally an infinite number of shades between light and dark. And then on the right, we've got digital data, which is discrete. It has very specific, separate values, kind of like a light switch that's either all the way on or all the way off. There's absolutely nothing in between.
And this visual just illustrates it perfectly, doesn't it? On the left, that analog signal is a smooth, flowing wave, which perfectly mirrors the continuous nature of analog data. But on the right, the digital signal looks more like a set of stairs. It just jumps between a limited number of fixed levels, which is the perfect way to represent those discrete on or off digital values.
Okay, so for the rest of this explainer, we're really going to focus on analog signals. And the reason for that is because even the most mind-bogglingly complex signals are all built from one very, very simple foundation. Let's go meet the atom of the signal world.
This right here is the sine wave. It is the simplest, most fundamental periodic analog signal you can get. Seriously, you cannot break this down into anything simpler. Every single other complex analog signal is actually just a combination of these simple sine waves.
So if we're going to be building everything from these sine waves, we really need to understand their basic properties. Every single sine wave can be described by three key characteristics, which we can measure and, more importantly, we can actually modify to encode information.
First up is amplitude. Now this is essentially the signal's strength or its intensity. If you think of a sound wave, amplitude would just be its volume. A higher amplitude means more energy. Simple as that. And you can see the difference so clearly right here. Both of these waves have the exact same rhythm, right? The same number of cycles over time. But that top wave has a much higher peak amplitude. You could say it's louder or just plain stronger than the bottom wave.
Okay, next up we have frequency. This is all about the rate of change of the signal. It's a measure of how many full cycles the wave completes in a single second. So if amplitude is the volume, you can think of frequency as the pitch, how high or low the note is.
And here you see it in action. That top signal is changing really fast. It's completing 12 cycles every single second, so its frequency is 12 Hertz. The bottom signal is way slower, completing only 6 cycles in that same second, which gives it a frequency of 6 Hertz.
And finally, we have phase. Now, this one can feel a little tricky at first, but it's really just describing the wave's starting position. It tells us exactly where in its cycle the wave begins at the very first moment, at what we call time zero.
This slide just makes it crystal clear. Look at these three waves. They all have the exact same amplitude and the exact same frequency. They're basically identical. The only difference is their starting point, their phase. The first one starts at 0 degrees, right at the baseline and heading up. The second one is shifted by 90 degrees, so it starts right at its peak. And the third is shifted 180 degrees, starting back at the baseline but heading down.
Okay, so we've got these waves with their amplitude, frequency, and phase, and we usually look at them as they change over time. But there's another incredibly powerful way to visualize these signals.
Exactly. That's the big question, right? When you start adding a bunch of waves together, trying to see how they change over time, it gets really messy really fast. So isn't there a more elegant way to represent all this information? Well, the answer is a definite yes.
And this slide shows us the solution. We can look at a signal in two different ways, or what we call domains. The top graph is the time domain. That's what we've been using so far. It shows the signal's amplitude as it changes over time. But look at the bottom graph. This is the frequency domain. It completely ignores time and instead gives us the super simple snapshot of what frequencies make up the signal. So here's the crucial point. That entire beautiful flowing sine wave from the time domain can be simplified into one single vertical line, one spike, in the frequency domain. The spike's position on the line tells you the frequency, and its height tells you the amplitude. It's just incredibly efficient.
And this is where it gets really powerful. On the left, in the time domain, you've got 3 different sine waves all jumbled together. It's a confusing mess. But look to the right. In the frequency domain, they become 3 clean, totally distinct spikes. We can see immediately that our signal is made of 3 parts, one at frequency 0, one at 8 Hz, and another at 16 Hz. It's like a cheat code for understanding complex signals.
Now, a single sine wave all by itself can't carry a whole lot of information. To send a song or a picture or a video, we need to combine a whole bunch of them into something way more intricate.
And that's called a composite signal. Using this amazing mathematical tool called Fourier analysis, we can combine thousands, even millions of simple sine waves, each with its own unique amplitude, frequency, and phase, to create one super complex signal that's capable of carrying massive amounts of information.
And of course, when you create one of these composite signals, you are by definition using a whole range of different frequencies. The width of that range, from the lowest frequency you're using to the highest, is what we call the signal's bandwidth. You can think of it as the width of the highway that all this information is traveling on.
And bandwidth has very real-world consequences. An AM radio station, for instance, only needs a pretty narrow highway of about 10 kilohertz to get its signal out. But an FM station, with its much higher quality sound, it needs a way wider highway, 200 kilohertz. And an old analog TV signal, carrying both sound and a moving picture, that needed a massive 5.5 megahertz of bandwidth. The bottom line is, more information always requires more bandwidth.
And that really brings us to the core takeaway of this entire thing. Every digital photo, every streaming movie, every single phone call, at the end of the day, it's all just an incredibly complex symphony, composed of countless simple sine waves, all playing together in perfect harmony to deliver information right to you. I mean, it's just an incredible thought, isn't it? This elegant system, built from the simplest possible waveform you can imagine, is the foundation of our entire digital world. It kind of makes you wonder, what other incredibly complex systems in our universe, maybe from life itself to the cosmos, are also just a beautiful symphony built from a few surprisingly simple rules?